Let us look at the second part of Chapter 2, Axioms of Probability. We learned about experiments, sample space, events, the union, intersection, and the complement of events in the first part. Today we are going to look at how to do calculations in probability. Before we do that, let's try to get an idea about what a probability is. We usually use probability, maybe without knowing that it is based on probability, in most of the time in our day-to-day life. Say, for example, a person may look around the surrounding and the environment and make a statement such as, there is high chance that it will rain today. Or maybe based on the previous experience and the train timetables, a person may say, there's a very little chance that the train will come on time today. In all these situations, you can see that uncertainty is there. So those are the questions where we cannot answer exact or clear-cut yes or no answers. In all these situations, we have the uncertainty and we use the words such as perhaps, maybe, sometimes, most of the time in order to express the uncertainty. Or in simple words, probability is the mathematical explanation of chance. So in those situations, we ask the question, what is the chance of rain today? Or what is the chance that the train will not be late today? So in order to answer these questions, we need the help of probability. When we calculate probability, we have to look at three different types. The first one is the empirical probability or the frequency interpretation. Here, the results are completely based on experimental outcomes and no assumptions are made. We usually denote the probability of an event A as P within parentheses A. If we perform an experiment n times and suppose we are interested about an event A. So let's say one trial of this experiment would result either A or A's complement. Now out of these n trials, suppose that event A of our interest occurred n times. Then the ratio m over n is proportion of time A will occur. So when n gets larger and larger, this ratio m over n approaches to a constant value. So this ratio or this approximation of m over n will be the estimate of the probability of the event A. So we can see that it is based on the large number of times of this experiment, or in other words, in the long run. So we say that the probability is defined based on law of large numbers. Let's look at the approximation of this ratio to the probability of the event using a very simple example. Now think about tossing a balance coin. You all know that when you toss a coin, there can be only two possible outcomes, that will be either head or tail. Okay, let's note down what will be the result by tossing a coin several times. Okay, so let's denote the toss, the number of times, and then whether the head appears or not. And then let's try to find the number of heads out of the total number of tosses. Okay. Suppose we tossed the coin for the first time and we got a head. So the probability of getting a head, or the ratio of getting head out of the total number of tosses, will be 1 over 1. Okay, now suppose we toss it for the second time and we got a tail. So H will be 0. Now there's only one head out of 2 tosses. So that ratio is 0.5. Okay, so let's do it several times again. So I'll say the third toss. Again you got tails, so no head. Still you have only one head out of 3, which is 0.33. For the fourth time you got a head. Now you have 2 out of 4 trials, 0.5. Now suppose the next one again you got a head. So you have 3 out of 5. Okay, you can find the ratio. And the next time no head. So altogether still you have 3 heads out of 6. So 0.5. This will be 0.6. The seventh one you got a head again. So that will be 4 out of 6, which is 2 over 3, 0.66. The next one. So this will be 7. Okay, you have to find the correct one. Another head. So you have 5 out of 8. Okay, you can find the value. Let's go for another one. Still 5 out of 9. And the next one, no head. So you have 5 out of 10, which is 0.5, and so on. So you can find this ratio. Now we did it only 10 times. Now suppose we want to draw this ratio, and we'll see how the graph will look like. Okay, in my y-axis, I'm going to represent the ratio m over n, or the number of heads out of the total. And on my x-axis, the number of trials, or the number of tosses. Okay, so we start with 1.5, then the value fluctuate around 0.5. So this one, second trial, third one, fourth one, fifth one, and so on. So you'll see the values, right? The 3, 5, 6, it will go like this. And if you do it many times, say for example 100 times or million times, you will see that this ratio will finally approximate to the probability 0.5. So that is why we say when you toss a balanced coin, the probability of getting head is 0.5 and the probability of getting tail will be 0.5. That is, the total probability 1 minus the probability of getting head will be the complement, which is the probability of getting tail. So you see that by tossing a coin only 5, 6, 7 or even 10 times, you cannot say that the probability of getting head is 0.5. If you want to prove that, you have to do the tossing many times, a very large number of times, maybe millions of times. So if you do that, you'll see that this fluctuation will finally approximate to 0.5. So not only for these type of experiments, now if you think about rolling a 6-sided dice, the probability of getting 1, we know that it will be 1 over 6. But how do we get that? That is by tossing the coin many number of times, large number of times, and getting that ratio 1 over 6 approximation in this long run. So that is why we say the probability is defined based on the law of large numbers. In order to get the probability of an event, you have to do that experiment large number of times. Now we have the subjective probability. These are the probabilities that we express based on a person's experience or knowledge. So we do not have any evidence to prove that. So if you think about the very first example, the chance of raining today, the answer for that question will be based on a person's experience and general knowledge. Then the last one, axiomatic probabilities. These are the probabilities defined as mathematical objects. So those are the behaviors according to a certain well-defined rules. Now let's look at those axioms of probability. Suppose that each event A of an experiment having a sample space S, there is a number denoted by PA. So that is the probability of A. So that will be according to the following three axioms. First axiom, the probability of an event is a non-negative real number. That is, probability of A is always greater than or equal to 0 for any subset A of the sample space S. Axiom 2, the probability of the sample space is 1. So that is, the total probability is always 1. So which means when you calculate probability of a certain event, it should be always greater than or equal to 0 and the total probability is 1. So which means the probability of A should always lie in between 0 and 1. So when you do calculations, if you end up with a value for a probability less than 0 or greater than 1, that means there is a problem in your calculation. So a probability of an event is always lying in between 0 and 1. The third axiom, if A1, A2, A3 is a finite or infinite sequence of mutually exclusive events in our sample space S, which means the pairwise intersections are empty, then if you want to find the probability of the union of these events, you can find it by taking the union of A1, A2 up to AN if it is finite. That probability will be the probability of A1 plus probability of A2 plus all the way up to probability of AN, or if it is infinite, n will go up to infinity. So we say PA as the probability of the event A. For these three axioms, we do not need proof, but if the resulting theory is to be applied, you must show that these three axioms are satisfied. Okay, let's look at an example. An experiment has 4 possible outcomes. So these outcomes are A, B, C, and D. They are mutually exclusive. Can you say why the following assignments of probabilities are not permissible? What do you think? In the first one, the probability of A is 0.12, probability of B is 0.63, probability of C is 0.45, and finally probability of D is negative 0.20. Do you think that these probabilities and then forming the sample space out of these events A to D will be a correct assignment? Probability of A, B and C are okay, but if you look at probability of D, you see a negative value. According to the axiom 1, probability is never negative. Therefore, probability of D having negative 0.21, this is a problem. So therefore, the assignment in the first set, this is wrong. Now let's look at the second one. You have the probability of A, B, C and D, 9 over 120, 45 over 120, 27 over 120 and 46 over 120. If you look at these ratios, all of them are in between 0 and 1. Now if this is a correct assignment, when you add these probabilities according to axiom 3, probability of A plus probability of B plus probability of C plus probability of D should be the probability of S, the whole sample space, O1. Now let's check whether The addition of 9, 45, 27 and 46 is 120. Okay, so if you do the calculation, you see that at the top you cannot have 120, so you will not get 1. So this assignment is also wrong. Okay. The probability of an event is a measurement that will occur on a scale from 0 to 1. Or you can represent it as a percentage, which will be from 0 to 100%. Let's look at the first theorem of the chapter. If A is an event in a discrete sample space S, then probability of an event A equals the sum of the probabilities of the individual outcome comprising A. So let's say the individual outcomes that comprise A are denoted as O1, O2, O3 and so on. So these O's are mutually exclusive from the third axiom. So A will be the union of O1, O2, O3 and so on. So the probability of A will be the probability of O1 union O2 union O3 and so on, which is the probability of O1 plus probability of O2 plus probability of 3 and so on, as in axiom 3. Let's look at some basic set operations. We say A minus B as the set of all the elements from A that are not in B. So we looked at this diagram in the part 1 also. So if you look at this colored or this shaded area, that is the area which contains the elements that are in A but not in B. So which is denoted as A minus B. We say two sets A and B are equal if A is contained in B and B is contained in A. So you see a common circle for both A and B. Next comes the distributive law. The first one is you have A union B union with C. This is same as A union with B union C. So you see that the parenthesis is shifted to the later letters. In the same manner, you have A intersection B union C. Now in this case, you distribute the intersection for B and then for C. So you have A intersection B and then the union A intersection C. The last one is exchanging the intersection to the union. So you have A union B intersection C, where you have A union B and the intersection with A union C. If you can remember the De Morgan's law, which is the A intersection B's complement is same as A's complement and B's complement by exchanging or interchanging the intersection to union. I have the other way around also, by interchanging union to intersection. So that is the De Morgan's law. If A is contained in B, we say A is in B. Then A intersection B will be A and A intersection B's complement will be empty. Let's try to explain this using a Venn diagram. Here's our sample space. It says A is contained in B. So we have B, the bigger circle, and A is inside it. If you look at A intersection B, that is the overlapping area. So that is exactly A. If we go to the next one, Let's use another diagram. Here's B and you have A inside it. We need A intersection B's complement. So let's try to color it. Here's A. Then we have B's complement. That is everything outside circle B. Okay. So we need intersection of these two colored areas. We see that they are never overlapping. So therefore, the intersection of A and B's complement is the empty set. Okay. Okay. Now let's try another experiment and see how we can calculate simple probabilities. If we twice flip a balanced coin, what is the probability of getting at least one head? So we want to find the probability of getting at least one head. Okay, let's start with writing down the sample space. We are flipping two balanced coins. So you may end up with head for both coins, head for the first coin, tail for the second, tail for the first, head for the second, and tail for both. Now remember, HT and TH, they are not the same. Since we assume that the coin is balanced, these outcomes are equally likely, which means all these events, all these outcomes will share the same probability. You know that the total probability is 1. Since there are 4 outcomes, the total probability 1 should be divided equally among the 4 outcomes. Therefore, the probability of each these sample points will be 1/4. If you add the probability of HH, probability of HT, probability of TH, and probability of TT, you have 1/4 added 4 times, making the total probability 1, or that is the probability of the sample space S. Now let's look at our event. That is getting at least one head. So let's try to write down our event A. At least one head means you may get one or more. So you may get 2 heads or only 1 head. That will be HT and TH. So there are 3 outcomes in our event A. According to the theorem 2.1, probability of A will be probability of HH, probability of HT, plus probability of TH. That is 1/4 plus 1/4 plus 1/4, which is 3/4. So we get the probability of event A as 3/4. Let's try another one. A die is loaded in such a way that each odd number is twice as likely to occur as each even number. You have to find the probability of event G, where G is the event that a number greater than 3 occurs on a single roll of the die. Okay, so we are going to roll a 6-sided dice, and we know the sample space is 1, 2, 3, 4, 5, 6. It says that each odd number is twice as likely to occur as each even number. So which means this die is not a balanced one. Which means all 6 faces does not contain the same probability or equally likely occurrence. On the other hand, each odd number is twice as likely to occur as each even number. So let's say probability of an even number is W. Just a notation. If probability of getting an even number is W, what will be the probability of getting an odd number? It says each odd number is twice as likely to occur as each even. So the probability of getting odd will be 2 times as even, which is 2 times W. Okay. Now if we find the probability of these outcomes, 1 is odd, 2 is even, 3 is odd, and so on. So you have the probability of getting 1, probability of getting 2, probability of getting 3, 4, 5, and 6. This should be the probability of the sample space, which is 1. So the probability of 1 is twice W. This is W. Again 2 times W. W. 2 times W. W. Should be 1. If you add these values, you will end up with 9W equals 1, which means the value of the variable 1 W is 1 over 9. Now our question is the probability of G, where G is the event that a number greater than 3 occurs on a single roll of die. A number greater than 3. So what is the event G? A number greater than 3 will be 4, 5, and 6. So we need the probability of G will be probability of getting 4, 5, or 6. Now this is from the third axiom. We get probability of 4 is W, which is 1 over 9. Probability of 5 is 2 times W, which is 2 over 9. Probability of 6 is again 1 over 9. So we end up with probability of G is 4 over 9. So that is how we calculate the probability of the event G. Now let's look at the second theorem. If an experiment can result in any one of n different equally likely outcomes, and if simple n of these outcomes together constitute event A, then the probability of event A is simple n divided by capital N. So this is actually the ratio that we talked in probability. Let's try to prove this theorem. Now suppose O1, O2 up to On be the individual outcomes in our sample spaces. So there are capital N number of outcomes in the sample space S. Each of them will have probability 1 over 9 because it says equally likely outcomes. Equally likely means all these n outcomes will have the same probability. Therefore, the total probability 1 will be divided equally among the n outcomes. Hence, each of these individual outcomes will have the probability 1 over capital N. Now, if A is the union of n of these mutually exclusive outcomes out of this capital N, and it does not matter which ones are they, so you can write probability of A as the probability of outcome 1 union outcome 2 up to the union of outcome small n or simple n. According to the third axiom, you can write this as probability of outcome 1 plus probability of outcome 2 all the way up to the probability of outcome simple n. We know that each of these outcomes, the probability is 1 over capital N. So we have 1 over capital N plus 1 over capital N, and we add it how many times? Simple n times. So you have 1 over n added simple n number of times, giving us the ratio simple n over capital N. So that is the proof of theorem 2.2. Okay, let's look at another example. This example needs knowledge about a standard deck of playing cards. You all know that a standard deck of playing cards contains 52 playing cards. These 52 cards will have two colors. You already know they will be either red or black, which means there are 26 blacks, 26 red, and these are divided among 4 different suits. The red ones are the diamond and hearts, and then the black ones will be spades and clubs. And we know each of these suits will contain 13 playing cards, which will add up to 52. So we are going to drop the jokers. We say that a full house occurs if your hand consists of 3 of a kind and a pair. So when you deal 5 cards from a standard deck of playing cards, we say it is a full house if these 5 cards are in such a way that there are 3 of a kind and a pair, which means 3 of these playing cards are from the same kind and the other 2 another kind. Now what is the probability that you end up with a full house if you pick 5 cards randomly from a deck of 52 playing cards? Let's see how we can solve this question. Say for example, a full house is 3 kings and 2 aces. So this is an example of a full house. So I have 3 kings, 3 of a kind and 2 aces. So how many ways are there to select 3 kings? You know that there are 4 different kings in the playing cards. Out of the 4, how many different ways that you can choose 3? So this is a combination. 4 choose 3. And how many possible ways are there to choose 2 aces out of the all possible aces? There are 4 aces. Out of them, selecting 2 aces, that will be 4 choose 2. So you have combinations here. So the number of ways to get 3 kings and 2 aces as the full house will be 4 choose 3 times 4 choose 2. Now this is only one possible way of getting a full house. Yes, so there are many other different ways. Another one is you get 3 tens and 2 jacks. So that is another full house. Again, there are 4 different tens from the 4 suits. We have 4 choose 3 and there are 4 jacks. Out of them you select 2. So likewise, you can end up with several number of possible different full houses. Okay. Now you know that there are 13 different kinds. Okay, so that will be starting from A, 2, 3, 4, up to 10, then Jack, Queen, King. So there are 13 different kinds. So in order to find 3 different kinds out of 4, so there are 13 possible ways. Okay, so there are 13 possible ways of selecting 3 out of 2. After you select them, there are only 12 remaining kinds. So to choose the pair, you have only 12 remaining kinds. Therefore, the total possible ways of selecting full house will be 13 times 12 times 4 choose 3 times 4 choose 2. So I hope this is clear. So this needs your knowledge about combinations and the multiplication rule. So again, it will be there are 13 different ways to select 3 of a kind. and also there will be remaining 12 to choose 2 out of 4. So that will be 13 times 12 times 4 choose 3 times 4 choose 2. So this is the number of possible full houses that you can get. Now if you go back to our question, it asks what is the probability of being dealt a full house. So if you want to find the probability of having a full house, you want to find what is that ratio out of any type of 5 different cards that you get from this pick. So without any condition, selecting 5 different cards out of 52, that will be 52 choose 5. So this is without any restrictions, and then probability of getting a full house will be out of this total 52 choose 2, you have your condition 13 times 12 times 4 choose 3 4 choose 2. So if you do this calculation, you will end up with 0.0014. So if you randomly pick 5 cards out of a well shuffled standard deck of playing cards, the probability of getting a full house will be 0.0014, or you may say 0.14%. There are a few other rules of probability that you can derive from these axioms. So we end up with the third theorem. If A and A's complement are the complementary events in a sample space S, then the probability of the complement of A is 1 minus probability of A. Okay, so let's try to prove this one. So here's our sample space S, and we have our event A. Everything outside A will be A's complement. Okay. According to the definition of the complement, A and A prime are mutually exclusive. That means they do not have any overlaps. And we know A union A's complement will end up with the whole sample space S. We know that the probability of the whole sample space S is 1, and if you want to find the probability of the left hand side, so that will be probability of A union A's complement. Now from axiom 3, the probability of A union S prime will be probability of A plus probability of A's complement. This is from the third axiom, because A and A prime are mutually exclusive. From that you get probability of A's complement as taking this PA to the other side, you get 1 minus PA. So that is the proof of theorem 2.3. The next one, fourth theorem, probability of an empty set is 0 for any sample space S. Now how do we prove this one? We know that the sample space S and the empty event are mutually exclusive, and also if you take the sample space union the empty set, you will still get just the sample space. So this will be probability of S union the empty set is probability of S, which is 1, and you have probability of S plus probability of empty set. This is from axiom 3, because S and empty set, they are mutually exclusive. Okay, so this is same as PS1. But we know that if it is empty, the probability will be 0. So we end up with probability, because the probability of S is 1. Probability of S is 1, which means the probability of the empty set is 0. You have to be careful. The probability of an event A equals 0 does not mean that A is an empty set. Next, we have the fifth theorem. If A and B are events in a sample space S and A is contained in B, then the probability of A will be less than or equal to probability of B. Okay, so let's try to prove this again using a Venn diagram. Here's our sample space, and we have A contained in B. I have the outer circle B and the inner circle A. We have to show that the probability of A is less than or equal to probability of B. Now, since A is contained in B, we can write that B equals A union S intersection in B. Let me correct it. So I'll explain it again. So this B will be A and the rest of the circle, which means B but not in A. We usually denote it as A intersection is complete. Okay, and since these two are mutually exclusive, okay, so A and A intersection B complement are mutually exclusive. I'm using the notation ME for mutually exclusive. We get probability of B as probability of A union A intersection B is complete. Then probability of B becomes probability of A union probability of A intersection B is prime, or rather you can say plus, right? So which means PB comes by adding a certain value to PA. This value is always greater than or equal to 0. This is from the axiom 1. Therefore, adding a positive value for PA becomes PB, which means PB should be bigger than PA. Okay. So that is the proof of theorem 2.5. Now let's look at the sixth theorem. It says the probability of an event is lying in between 0 and 1 for any event A. So if you look at the proof, we know that event A will be in between an empty set over the sample space. By applying the probability for all these three events, we get probability of the empty set, probability of A, and probability of S. By the previous theorem 2.5, because empty set is contained in A and A is contained in S, you can use the less than or equal sign. So this is from the proof of the previous theorem 2.5. But we know that the probability of the empty set is 0 and probability of the whole sample space is 1. Therefore, we end up with probability of A is in between 0 and 1. Now, if you look at the third axiom, it is also known as a special addition rule. So, for any two events A and B, the general addition rule can be defined as the theorem 2.7. If A and B are any two events in a sample space S, the probability of their union will be the probability of each event separately and then subtracting the common outcomes. So this is called the general addition rule. So we get probability of A union B equals probability of A, probability of plus probability of B minus probability of A intersection B. Now let's try to prove this. So again, I'll use a Venn diagram. It is easy explaining when you have a Venn diagram. Here's my sample space. And we have the two events A and B. To make this proof easy, let's denote each of these areas as simple A, simple B and simple C. So this part colored in blue, let's say that is A, simple A. The overlapping area, our intersection, as B. And the next area as C. Okay. So we have A intersection B, that is B. A intersection B's complement, that is only A. And B intersection A's complement, that is C. So the probability of A union B will be A plus B plus C. So these are the probabilities. Okay, so let's try to combine this as A plus B and C plus B by adding an extra B. So if you want to add extra B, you have to subtract it. So this is like nothing has happened. So what we have done is we add and subtract simple B to our expression. So if you add and subtract the same value, that means it is like nothing has happened. We know that A plus B is probability of A, the circle A. C plus B is the whole circle B. And then subtract the B. B is where you have the overlap or the intersection. So that is exactly the addition rule. So if we explain it this in words, if you need the union of A and B, you add everything in circle A, then you add everything in circle B. When you do that, this overlapping area, the red area or B, is added twice. That is why we subtract it once. So that repetition of the overlapping area will be removed. So you get the general addition rule. Here is a simple example from the addition rule. In a large metropolitan area, the probability that a household owns a color television set, black and white set, or both of them are 86%, 35% and 29% respectively. You want to find the probability that a family owns either or both kind of sets. So which means the union of a color television or black and white. So let's denote our events A as if the family owns a color television. B, if the family owns a black and white set. We want to find the probability of A union B. That means it owns either or both. Right? So that is the A union B. If you use the simple addition rule, general addition rule, here is the equation. A is when you own a color television, so probability of owning a color television is 0.86, it's given there. And a black and white one, probability of event B is 0.35. Then both of them is 0.29, so you have 0.86 plus 0.35 minus 0.29. So if you do this calculation, you'll end up with 0.92 or 92%. So when you do calculations in probability, you have three options to record your answer. It can be either a decimal value or a percentage or a ratio. So if you get, for example, the probability of let's say an event D, the answer is 1 over 4. You can leave it as 1 over 4 or as 0.25 or as 25%. So either of these answers will be okay. Okay, the next one is to generalize this theorem 2.7 for any three events A, B and C. So that will be the probability of A union B union C is the probability of A, B, C, the original events. Then you subtract the intersections of 2's, A and B, the pairs, A and C, A and B and C. And then finally you add the overlapping of the all three areas. Okay. Now the proof is there. You can study it by yourself and get the idea. It will be easy if you draw a Venn diagram and check this proof. So here you have three different circles, A, B and C. Okay, and see whether you can understand this proof. Okay, so let's look at another example. A society needs to form a committee of 5 among 10 members. So altogether there are 10 members. Out of them, you want to form a committee of 5. Inside these 10 members, there are 6 males, so the rest will be females. So your members 10, there will be 6 males and 4 females. You want to find the probability of selecting a committee if there must be 4 males and 1 female. The second one, there is always more males than females. The last one, there must be at least 1 female. Now in order to answer this question, you need your knowledge about combinations and also the knowledge about probability. Okay, so let's start with the number of ways of forming a committee of 5 out of 10 without any restriction. Okay, so without any condition, the number of ways to form a committee of 5, that will be selecting 5 out of 10. So that is 10 choose 5. Oh, these are the combinations. NCR 10 minus 5, 5. Okay, you can find this value. Let's look at the first one, part A. You need your committee to be 4 males and 1 female. It must be 4 males and 1 female. So how many possible ways to select 4 males? You know there are 6 males. Out of these 6, in order to find 4, you have 6 choose 4. And then you have to choose 1 female out of the 4 females. Okay, so this is the number of possible ways to form a committee with 4 males and 1 female. And the probability of that will be, if you divide this by the total number of committees that you can form without any restriction. Okay, so this will be the answer. You can find the calculation, do the calculation and find the final answer. Now let's try the next one. There's always more males than females. Okay, so there will be several possibilities for that. Remember, you have to have 5 members in the committee. There's always more males than females. Okay, so maybe you have all males and 0 females. Since there are 6 males, you can do that. Or you can have 4 males and 1 female, 3 males and 2 females. If you go to 2 males, you'll get 3 females. That violates the condition. Always more males than females. So these are the 3 possible ways. So for the first one, you have to choose 5 males out of 6 and 0 out of 4. Okay, you can find the value. The next one, you have to choose 4 out of 6 and 1 female out of 4. And the next one, you have to choose 3 out of 6 and 2 out of 4. Okay, so you have to find these values, and okay, whatever the answer you get here, let's say A, answer is B and C, you have to add them together. So A plus B plus C out of the total 10 choose 5. So that is the probability of having a committee where there are more males than females. You can easily calculate these combinations and then add them together. Remember, here you have the multiplication and then you have the addition. Okay, so out of that you have to divide by 10 choose 5. Okay, the last one, there must be at least 1 female. So there must be at least 1 female. How do we do that? Again, let's try to list down males and females. There should be at least 1 female. So at least 5, or it can be more. Okay. So 1 female, then there must be 4 males because you have to have 5. If there are 2 females, you have to have 3 males. You can have 3 females, then there will be only 2 males. But there can be 4 females, there will be only 1 male. That's all because there are only 4 females. So there are 4 possible ways to have this type of committee. So again, you can have 4 males and 1 female. 6 choose 4 times 4 choose 1. You can find the answer. 6 choose 3. 4 choose 2. You can find the answer. 6 choose 2. 4 choose 3. You can find the answer. And finally, 6 choose 1. 4 choose 4. The answer. Then you add them together. Then the probability of having such type of a committee is divided by 10 choose 5. So this is how you answer questions like this. That needs your knowledge on combination. Okay, so here's the last question. A lottery ticket consists of 4 numbers and a letter from the English alphabet and a zodiac sign. You are familiar with these type of lotteries. For example, Govisata. You have 4 numbers and then you have a letter in front of it, and then you have 1 zodiac sign. There are 12 zodiac signs, you know. Out of them, 1 will be selected. The 4 numbers are selected from a machine that contains all 80 balls. You know, they place these ping pong balls inside the machine, with their number printed on it. So there are 80 such balls. So from this machine they choose 4 balls, one at a time. Okay, so this is a single machine. So there are 80, you choose one, you're not going to put it back. You pick the second one, you're not going to put it back, and so on. So you have to find how many possible ways to get the first one, the second one, third and the fourth. And then there are 26 possible ways to get the letter, 12 possible ways to get the zodiac sign. So I'll leave this as an exercise for you. Try to find the probability of winning the grand prize. If you do this calculation, you will find that that probability is a very, very small number. So try to find the answer for this one and see whether you can find the probability of winning the grand prize.